Hi, my name is Julia Hesse. I'm a postdoc at IBM Research in Zurich. This talk is about password authenticated key exchange, or PAKE for short. I'm going to show you an impossibility result, which implies that the two versions of PAKE, symmetric and asymmetric, cannot be obtained from the same minimal assumptions. So let's start with an introduction to asymmetric PAKE. Have you ever wondered what happens when you log into an account created at some website? Does Make Friends here actually see your password in the clear when you hit submit or next? The magic protocol that makes the actually entire web work is called password over TLS. So let's have a look at it. Suppose Alice wants to log in at her account at Make Friends. She would first establish a secure connection to the Make Friends server using TLS. Afterwards, she uses the resulting secure channel to transmit her password to the people at Make Friends. Their server, which has Alice as a registered user, verifies whether the password is the one that Alice provided earlier when she created her account at Make Friends. So, depending on the outcome of verification, Alice is then either granted access to her account or not. This works well. And as I said before, this is how most sites actually handle password logins. Regarding security, the TLS channel protects Alice's password from being leaked to an eavesdropper or to a fraud server. The clear downside of this protocol, however, is that Alice tells her password to Make Friends upon each login. And this handling of clear text passwords is obviously suboptimal, since the password might get compromised while being processed at Make Friends. So let's see how we can prevent sending clear text passwords. We start by outlining the formal requirements of the setting. We have Alice on the left and the server at Make Friends on the right. So Alice holds a password, and she previously generated an account at the Make Friends website, so at the server. The server stores some object containing Alice's password. For example, you can think about this object as a salted hash of the password. Now we want to run a protocol that tells Alice and the server at Make Friends whether Alice remembers her password correctly when she later wants to log in to Make Friends. Security-wise, we demand that this protocol run leaks nothing to neither of the parties. The cryptographic solution for this setting is called Password Authenticated Key Exchange, or PAKE for short. This primitive basically enables Alice and Make Friends to figure out whether the password stored at Make Friends is equal to the one that Alice uses upon login. If these passwords match, both Alice and Make Friends can compute the same high entropy session key K. On the other hand, if passwords mismatch, then both compute randomly looking keys. This protocol can easily be extended to let both parties learn the outcome of the password matching by sending key confirmation messages. Okay, so now let's look into more details regarding security of a PAKE. First, let me issue a warning. An adversary can always guess Alice's password with non-negligible probability. In practice, anybody can go to the Make Friends website, type Alice's username, and attempt to guess her password. This would work eventually, since human memorable passwords come from what basically we as cryptographers would consider like a small and efficiently searchable space. So we cannot really ask for the scheme to prevent the adversary from succeeding in his attack with all but negligible probability. Instead, we will demand that the password guess is the best possible attack. So this slide shows a more detailed list of security properties of APAKE. First, we consider an honest server, meaning that the server follows the protocol, and also the server safely stores Alice's information, so there was no like leakage of password information to the adversary. As we said before, it's always possible to attempt to log into somebody's account by just guessing the password. So we want to ensure that this so-called online dictionary attack is the best possible strategy. And for this, we simply asked for an upper bound as well. So we asked that exactly one password guess is possible per run of the protocol. If the server is compromised, we assume that there was a security breach, so Alice's account information is leaked to the adversary. In APAKE, this account information is usually called a password file. So you can think of this basically as a file containing salted hashes of passwords, for example. So now the adversary can try to figure out which password was used to produce Alice's file. For example, by just computing hashes, salted hashes of passwords. This is computationally feasible due to the number of passwords being polynomial. So APAKE security actually demands that the adversary still has to invest a certain amount of computation to crack the file. Next, we come to a crucial property, which is good news for internet users. We ask from an APAKE that the people that make friends do not learn which password Alice used upon login. They only learn whether she basically used the one she registered with or not. And last but not least, we require that output keys look pseudo-random. This is very common for key exchange protocols. So let's have a short look at existing security notions for APAKE. There are two security notions in the literature. On the left, we have a game-based notion by Benhamouda and Poinchevoix, which considers a multi-user setting and an adversary looking at executions with randomly chosen passwords. This notion has been introduced in 2013 and it has not been used much ever since. On the other side, there's a simulation-based security notion by Gentry, Mackenzie, and Ramzan from 2006. They use the universal composability framework by Kennedy. And since this framework comes with a nice composition theorem, it is only necessary to consider an adversary looking at only a single session, so one client and one server. Furthermore, this adversary can choose arbitrary passwords as input to this session. So it can choose related passwords, like very close passwords, or malformed passwords. And this is the notion that has been widely adopted for APAKE, and this is also the notion that we will focus on in this talk. So I have to show you a bit of details about the universal composability framework in order to explain the result of the paper to you. But I try to do it with pictures and very short. So to those of you not familiar, let's have a quick look. To consider security of, for example, an APAKE protocol in this framework, we first define an ideal version of APAKE. Ideal in the sense that, so it's this blue box on the right here. So this ideal blue box basically takes the input of the parties and securely computes the outputs and hands them back to the parties. This is what we call an ideal functionality in the UC framework. And this functionality might also provide leakage or allow influence by an adversary. So this is modeled via the red channel. So overall, the execution on the right is called the ideal world execution. And note that there is no direct communication between the parties. The parties just communicate with the ideal version of PEG, so this blue box. On the other side, on the left, there's the real world. So this is the real world execution of an APEG protocol that is running between two parties. The adversary may observe and tamper with the communication channel between these parties, so the message is sent around. Further, the adversary might decide to corrupt parties to learn their secrets. The UC security notion now demands that both executions cannot be told apart by a distinguisher who gets to choose the inputs of the parties and sees their outputs. The distinguisher might also or may also talk to the adversary, instruct him, for example, to report messages that are sent on the communication channel or to tamper with them. The task of the simulator on the right side, the guy with the glasses here, is basically to make the ideal execution look exactly like the real execution. Or not exactly, you can also say that you want them to look computationally indistinguishable, or any notion of indistinguishability. So among other things, the simulator needs to simulate a protocol transcript because in the ideal world, there's no communication between parties. And he has to do this basically without knowing the secrets of the parties, which in the case of APEG is their passwords. So let's look at the ideal version of APEG that is defined in the UC model. So this functionality has two phases, basically. The first above the blue line is the registration phase where Alice gives her password. The functionality now safely stores this password. And the second phase is the actual key exchange phase. This can be repeated many times. And Alice inputs a password again, basically her login password. And depending on whether these passwords match or not, the functionality now securely computes the output keys of the parties. As I said before, this output key is the same high entropy key if the passwords match, and if not, both outputs are random. So to enable the use of low entropy passwords as input to the protocol, we need to relax the functionality by allowing that the aforementioned types of dictionary attacks. So first consider a compromised server leaking a password file. The file does not really exist as an object in this ideal world. Instead, the adversary is allowed to submit arbitrarily many password guesses to the functionality, which replies with yes or no, basically depending on whether the guess matches Alice's registration password. The second type of dictionary attack is the online dictionary attack, and that we incorporate by allowing the adversary to issue exactly one password guess against either Alice or the server per run of the protocol. So per run of the lower part of the protocol. So per run of one key exchange. So protocols that are secure with respect to the APEG, this APEG functionality that we just saw, can be found in the literature. The main drawback that basically unites all of them is their use of idealized assumptions. Idealized assumptions can be, for example, a programmable random oracle, which is an oracle that implements a truly random function, with the simulator being allowed to determine arbitrary point value entries as long as they are not already taken. So hence the name programmable. Such an oracle cannot be instantiated securely, of course. On the contrary, you see secure symmetric versions of PEG where both parties hold clear text passwords, so where we have no password file, but also the server would take the role basically of a user having a clear text password. Here we have instantiations already in the standard model. So now let's come to the results of this work. Until today, it is still unknown whether the need for idealized assumptions is inherent for UC secure APAC. And note that answering this question, whether it's inherent or not, would require us to basically essentially rule out existence of UC APAC from arbitrary standard assumptions. So this seems hard. Instead, what we show in this paper is a separation result. So we rule out the construction of asymmetric PAIC from the same assumptions that are enough for obtaining symmetric PAIC. In more detail, we show that a non-programmable random oracle, which gives access to a truly random function that cannot be influenced in any way by the simulator, such an oracle does not help in constructing a UC APAC. And we also show that there is no UC APAC in a common reference string model. So a common reference string is a random-looking string that can be programmed by the simulator, but it turns out to be just not adaptive enough for these purposes. I will show you more what I mean with adaptive enough on the next slides. In the 20 years of its existence, there have been many impossibilities shown in the UC framework. A famous family of such impossibility results is the so-called commitment issue. This refers to a problem in the simulation where the simulator needs to commit to a value that is unknown to him, for example, when simulating a ciphertext for an unknown message. So let us see now how commitment issues help us proving things about APAC. So remember that in our APAC functionality, the distinguisher is allowed to provide the input password. Now we assume a distinguisher who lets an honest Alice register with make friends using password PW. Then the distinguisher instructs the adversary to compromise the server at make friends, which essentially means that the distinguisher says, okay, give me the password file, which now should contain Alice's password. So what happens in the real world? On the left-hand side is the real world. The adversary reports the password file value to the distinguisher. In the ideal world, to make things look indistinguishable, upon compromise of the server, the simulator wants to output a password file as well. However, the server in the ideal world has not really done anything so far, since the password registration, as I showed you before, essentially happens within this ideal APAC functionality, so within the blue box. This essentially means that the simulator has essentially no information whatsoever about the password that Alice used to register, despite his interface for offline dictionary attacks at the blue box that he can now use. So remember, offline dictionary attack means that he can make an arbitrary amount of password guesses on the registration password of Alice. The impossibility result that we show essentially follows from two observations now. First observation is that after obtaining the password file, the distinguisher can essentially deterministically check whether Alice's password is contained in the file. There's many ways to do this. Depending on the protocol, you could say, okay, he can hash the password along with the salt and see, so basically recompute the file. A check that essentially works with any APAC protocol is that the distinguisher can take the password and the password file, run the APAC protocol offline with these two inputs, and see whether the output keys are the same. If the output keys are the same, the password was the one used for creating the password file. The important thing to realize here is that the simulator essentially has no influence on this check anymore. As I said, the protocol can be run offline by the distinguisher without any interaction with the simulator. And why doesn't the simulator have any influence? We said that we have oracle access to a random function, but the simulator cannot program, so he has no influence on the values anymore. And essentially, the distinguisher can perform the check on the password file without talking to the simulator again. So the second observation that is needed for the impossibility result, so essentially for showing that the simulated password file will not be computationally indistinguishable from the password file in the real world. The second observation concerns the simulator's offline password guesses, so the interface that he can use when the server is compromised. So essentially, we need to make sure that the distinguisher somehow detects too many password guesses by the simulator. And this is basically a runtime thing. So in the UC model, we will have a mean to restrict the computational time of the simulator. Basically, we demand that the computation time of the simulator be close to the computation time of the real-world adversary. Okay, so after seeing this impossibility, we could now ask whether UC secure APEG is the wrong notion. So we showed that non-programmable random oracle is not enough to obtain UC APEG, and the non-programmable oracle is already an idealized assumption that cannot be instantiated in the real world. So our results basically provide strong evidence that idealized assumptions are, even stronger idealized assumptions are required by UC APEG. And these strongly idealized assumptions, they do provide the simulator with unrealistic leverage, so basically superpowers to program oracles or learn secrets. So what is the point of having a simulation-based notion in the first place when we then cheat to get the simulation through and tell the simulator secrets and give him superpowers? So is this the right notion or not? And with this slide, I want to convince you that UC is still the right model to analyze your APEG protocol. There's many reasons for it. I'm only mention a few of them here. UC is still the only model, or the APEG functionality defined in UC is still the only model that considers adversarially chosen passwords, which is the only realistic setting for APEG if you think about it. The analysis is also simplified because you only, in UC, thanks to the composition theorem, you only have to look at one session. So you can spare the hassle of analyzing multi-session security. Which is obviously the right setting for APEG, or the realistic setting for APEG, which will be run with like thousands or millions of users. Lastly, the usage of idealized assumptions does not make the proof of security meaningless. Essentially, a successful attack on the APEG protocol that we proved secure with respect to this functionality, an successful attack must exploit the instantiation of the idealized assumption. So in this case, of the random oracle. There's more results in the paper, so I encourage you to have a look. We provide several fixes to the APEG functionality of 2006. We prove security of an APEG called the Omega protocol, and we have some implementation considerations for multi-session APEG. And with this, I want to motivate you again to use Asymmetric password authenticated key exchange. Have a look at it. It's a very cool primitive. Spares you from sending your clear text password over the TLS channel to the server, and it integrates nicely with protocols such as TLS 1.3. Thank you for listening.